the basic difference between AC and AC. So this is the DC circuit, this is the AC circuit. Now, when you compare these two networks, it's a simple circuit. There is a voltage source connected to a resistor. And because it's a closed path, the current is flowing in each of these resistors. Now here, first note the difference between this voltage source and this voltage source. What's the main difference here? We have a voltage represented as capital V. This voltage V is a small v and it varies with respect to time. It's a function of time, V of t. So it is time dependent. So AC voltage source here is time dependent. Next, what are the other things about the voltage source? Here you can see plus here, minus here, which means the polarity of the voltage of the DC is fixed. It's fixed at one value, the polarity. Whereas here there is no polarity indicator, which means that the AC voltage will not remain at the same polarity throughout. And once again, the current here is capital I, which is a constant value. The current here is I of t, which means the current varies with respect to time. So now coming back to the graph here, this is the time with respect to the magnitude here. So we see here voltage is fixed magnitude, same value of voltage throughout the time. Similarly, the current value remains the same throughout the time. And in this case, it is all positive. They remain constant. It's only a straight line. Coming here to the AC voltage, here we have constantly varying magnitude. So in this, I say at some time, this is the magnitude T1. At some other time T2, the magnitude is different. And similarly, the voltage and the current remains at the positive value. This is the positive value here, and this is the negative value here. So it remains the positive value for some time. At some other time, it remains at a negative value. So that means the AC is not of constant magnitude as well as polarity. The polarity of the AC keeps varying from time to time, and the magnitude also varies with respect to time. So therefore, this is represented as V of t and I of t. They are actually the instantaneous values. Instantaneous values means the value of the quantity at any instant of time. So now you can now visualize the meaning of AC, that is alternating current. What is an alternating current? It alternates between positive and negative values. That's why it's called an alternating current. Now, are you familiar with this shape? What does this shape represent? This shape represents a sine function, or you can say a cos function. So that means the AC is basically a sine wave. So we will now see into the basics of sinusoids, or what are the characteristics of a sinusoidal function. We will now take the basics of sinusoid. So sinusoidal function is the one where any function y varies with respect to cos theta or sin theta. So we have here, for example, if you take sin theta, here we have sin of 0 is 0, sin of pi is 0, similarly sin of 2 pi multiples of pi is 0, and at pi by 2 obviously sin 90 is 1. So at pi by 2 we get the maximum value. Similarly, at this value we get maximum value, and this is a pattern which is repeating throughout. Now we have drawn this V of t with respect to omega t. What is omega t? It is nothing but angle theta. Theta is what? Angular displacement. Omega is angular velocity multiplied by time will give you theta angular displacement. The same thing can also be represented with respect to time here, and in this case we have something called a capital T, which is a period. We'll see more about the period later. So the general mathematical expression for a sinusoidal waveform is given by, in this case we are representing a voltage waveform. So we write V of t is equal to Vm sin of omega t plus or minus phi. So what is this Vm? The maximum value that is attained by the AC waveform, and then sin of omega t. Omega t is actually the theta function, and then this phi is something called a phase angle. We'll see more about the phase angle later. So this is a general expression for a AC quantity. So similarly, if we have a current also, we can write I of t is I of sin of omega t. So the AC has a amplitude and it has a angular velocity, which is nothing but the frequency, and then there is a phase. This is the phase angle actually. It has a phase angle. Now we'll see more about the characteristics of sinusoidal waveform. Now coming here, this represents a sinusoidal waveform. I have taken one complete waveform. After this, the pattern repeats. So we have certain terms here. One complete waveform is called one cycle. One cycle is one complete pattern of the waveform. One full waveform is called one cycle. And the time taken for one complete cycle is called the period, capital T, which we saw in the previous slide. So period is the time taken for one complete waveform. If you study this waveform here, what do you observe? We know that it's instantaneously varying, the magnitude keeps on varying with respect to time, and it remains constant for a particular period and remains positive for a particular period and then becomes negative for a particular period. So therefore we have a positive half cycle and a negative half cycle. So for one half of the cycle it is positive and another half of the cycle it is negative. So that means the positive half and the negative half are divided into two equal time periods, and which means we can say that the AC is a symmetrical waveform. Now we have a positive half and a negative half, and we have learned what is a time period, and the time period consists of two alterations, two polarities. One is the positive half and the other is negative half. So it consists of two alterations. We know that the time taken for one complete cycle is the period, and alternating current is nothing but a cycle, a positive and the negative half repeating continuously for a series of cycles and keeps on repeating. We have already seen the general expression for a sine wave. The same thing it is put here like this because we know this 2 pi f is nothing but omega. Here it is given. The angular speed is 2 pi f, which depends upon f is the frequency. What is the frequency? The frequency is number of cycles taking place in 1 second. We know that the AC is a cycle of waveforms like this. It keeps on moving. So how many cycles we have in 1 second? If you take 1 second, so the cycles in 1 second is called the frequency. In Australia, this frequency f is a fixed value which is 50 Hz. Whereas if you take the US, it is 60 Hz. In Australia, it is 50 Hz. So what does 50 Hz mean? That means the AC waveform has 50 cycles in 1 second. That's a transmitted AC signal in Australia. So it is 50 cycles per second. The unit of the cycles per second or units of frequency is called Hertz. H is that Hertz. Now we also know that the time period, what is the time period? The time period is the time taken for one complete cycle. This is the time period. So therefore, when you have number of 50 cycles in 1 second, then obviously in 1 second there are 50 cycles, or for 50 cycles it takes the time of 1 second. So that means for 50 cycles it takes 1 second. So therefore for 1 cycle, that will be actually the time period T. So the T is nothing but 1 by 50. So 1 by 50 is 20 seconds. So the time for 50 cycle signal is 20 seconds. Next is measurement of AC quantity. Now when we go into a DC quantity, we know that the DC is a fixed magnitude and it has the same polarity throughout. So when you say a DC of 5 volts, which means the voltage value is 5 volts throughout the time period. For any time, it is always 5 volts. So we can say this particular voltage measures 5 volts DC means we can understand what is DC. Now if you take a AC signal, if you want to measure a AC signal or if you want to represent a AC signal, how will you say? You cannot say 3 volts at this particular time. It keeps on varying. It depends on at what time you switch on the AC signal also. So therefore, it's very hard to give some value for the AC quantity. So therefore, there are various means of measuring the AC quantity or various representations for giving a value for the AC quantity. One is the peak value. So what is the peak value? The peak value is the maximum value that the wave takes. So it is a sinusoidal function. For a sinusoidal function, sin 0 is 0, sin pi is 0, or sin 180 is 0, and you have here sin of 90 degrees, which is pi by 2. So at that point, it is maximum value. So this is called a peak value. We have been seeing so far, this peak value is given by Em. So the peak value is the maximum voltage of the current which takes place at one particular instant of time. In this case, because it is a sine wave, this will be pi by 2 90 degrees, and then here we have 2 pi 360 degrees. That means the negative peak occurs at 270. So therefore, there are two different peak voltages appear at two different points. One is positive, another is negative peak, and then the positive peak occurs at 90 degrees and the negative peak occurs at 270 degrees. And what about the magnitude? This is minus Em. So that means magnitude wise they are equal in magnitude, they are only different in polarity. Now the peak to peak, another way of measuring is peak to peak. What will be the peak to peak? This will be Vm here, this is also Vm here. So the peak to peak value of AC quantity is 2 Vm. So we can either take the peak value of AC quantity or the peak to peak value of AC quantity. This is one way of representing AC. What is the other way? The next value is called the average value. So the average value, what's the general definition for an average value? The average value is the one which is the mean. That means the sum of all the values taken divided by the number of values. So if we have say 3 values, x1, x2 and x3, the average value is x1 plus x2 plus x3 divided by 3. That is the average value. So the same thing holds good here also. It's actually the average of all the instantaneous values taken over a cycle. So we are bothered only about one cycle because the cycle is going to repeat. The same pattern is going to repeat. So we'll take one cycle. So the average of all the instantaneous values taken over one particular cycle is called the average value, which means it is nothing but the cross areas here, area under the sine curve. The average value is nothing but the area under the sine curve. If you see directly here, what can you observe? This is a positive half cycle and this is a negative half cycle, and we know that the positive and the negative half is exactly equal. We already have seen that the AC is a symmetrical waveform. So when you take the average value, this will have some area, this will have some other area. So sum of these two areas is actually, because this is positive value, this is negative value. So actually in the sine wave, since it is positive and the negative halves are identical, the average value is 0. So how to calculate the average value of a sine wave? So let us first see the mathematical expression. We can actually, it's easier to put it this way, area under a curve divided by the time period, because we know this is for one cycle the time taken is T, capital T. So area under the curve divided by the time period, or we can say this average value is integration. Area is nothing but the integral function. So integral of V of t dt over a period 0 to t, this is the time period 1 by t. So 1 by t integral, because 1 by the time period, so we have 1 by t here, and this area under the curve can be represented in a integral form. It's always not easy to measure the area under the curve. It's easier to go by integration when you have different shades of a curve. So this is the general formula for the average value. Now we know that for a AC signal the average value is 0, which means we should find out some other way to calculate the average value. In the case of AC waveform, for which the positive and the negative halves are exactly symmetrical to each other, then we may have to compute the average value only for half the time period. That is for a time of t by 2. That means we are taking only one half of the cycle. So therefore, here we take only this cycle and we will calculate the average value for this period alone. So therefore Therefore, we have area under half the cycle divided by T by 2, or in the mathematical form 1 by T by 2 integral 0 to T by 2 V of T, or 2 by T 0 to T by T V of T into. Let us take the typical sine wave and calculate its average value. So as per the definition, we have average value is the area under the curve. Now since the sine wave is a symmetrical wave, we take only the area under one half of the cycle. That means we are going to find this area alone over a period of 0 to T by 2. In this case, T is actually 2 pi. The angle corresponding to T is equal to 2 pi. So for T by 2 it is pi. Therefore we take average value is 1 by T by 2, which is pi. Integral 0 to T by 2 is again pi. Dm sine of omega t into d of omega t. So here actually the d of t is equal to dm sine of omega t. It is simple sine function, isn't it? So when omega t is equal to 0, we have 0. When omega t is equal to pi by 2, we have dm, similarly like that. So this is a simple expression for a sine wave. Now how will you integrate that? If dm is constant, or take dm outside, divided by pi. Sine of omega t, integral of sine of omega t is minus cos of omega t. The integral limits are 0 to pi. So when you apply, you actually get here dm by pi. I'll take the minus outside because we have a minus. Here we have cos of pi minus cos of 0. So what is cos of pi? Cos of pi is minus 1. Minus here already we have this minus here, and cos of 0 is 1. So minus 1 is minus 2, and this minus will become plus. So we have plus 2 dm by pi, which other words we can have it as 0.637 dm. So that means first value we measured was a peak value. For a sine wave, the peak value is dm. When you take the average value for a sine wave, the average value is only 63.7% of the peak value, which is the RMS value, or it is called the effective value. So what does RMS indicate? Root mean square value. So we will see why it is called the root mean square value now. RMS value is, average value is what? The area, simply the area under a curve, given curve. Or it is the sum of all the instantaneous values divided by the number of instants we are taking those values. If you simply take an average value of the AC waveform, it will not give much sense. Or what we want is, we want to represent the AC as a quantity similar to a DC value. So therefore we are going for something called the RMS value. The RMS value actually compares the heat produced by a equivalent DC network. So let us say we have a DC network here, we have a AC network here. We pass some AC voltage E of t, which will generate a current, say I of t. So if we pass this I of t through some resistance R, what will happen? It is a current flowing through the resistance R. Obviously, this current will produce a power loss or a heat, I squared into R. Okay, so this is the heat or the power loss in the resistor, because power in a resistor actually produces only heat. So it's I squared into R. Now what we will do is, this is the heat produced by the AC. Now we have to compare the heat produced by the AC with that of the DC, and we have to find out a DC current which will produce the same amount of heat in the same resistor. So that means we can call that particular value of AC as a RMS value. What we do here, the equivalent value of DC that produces the same amount of heat or power in the same resistor actually as that of a sine wave or a periodic wave. So we are actually comparing what? The power. Power is, in this case, is the average power. So the power produced by a DC current is R into I squared DC, and power produced by AC is R into IRMS. In this case, it becomes IRMS. So this is the RMS value. The RMS value is that value which will produce the same amount of power as that produced by a DC current, equivalent DC current. So therefore, in this case of RMS, we are actually taking the average value of the power. So as per the average value, P average is 1 by the time period 0 to t, P of t into dt, where P of t is the instantaneous value of the power. What is power in a AC? It is, we just saw I square of t into R, square of the instantaneous current at any time, into R into dt. So when you integrate this, what will you have? This R is a constant, so take the R outside, 0 to t I square t into dt. Now this is the average power, which is actually equal to IRMS square into R. So I equate that to this value from there, and comparing these two equations, we get IRMS square is equal to 1 by t, this R and this R will get cancelled here, so 1 by t integral of I square dt into I square t into dt. Or we can say IRMS is root of 1 by t integral of I square t into dt. So it is the root mean square value. Because why do you call it a mean? Because we are calculating it from the average power. Average power is nothing but the mean of all the values. So it is root mean square value. We are squaring the current or the current and therefore finding the value. So it is called the root mean square value. Or it is the best value for representing a AC signal, hence it is called the effective value. Now how to calculate the RMS value of a AC signal? That is the sinusoidal signal. So we have a sinusoidal signal here. And now what do you do in RMS value? RMS value, we square it, we square the current, and then we take the root and then we take the average. So we square each and every point. So 0 becomes 0. At pi also it is 0, so at pi it is 0. At 2 pi it is 0, and then at 3 pi when we square it is 0. Now this Vm at pi by 2, the center, when you square that it becomes Vm squared. So this at it becomes Vm squared. Now at 3 pi by 2, that is 270 degrees, we have a negative of Vm. So when you square this minus Vm, it becomes plus Vm squared. So once again at 3 by 2, it is plus Vm squared. So this is a squared waveform of a AC signal. Now in the squared waveform, once again, when you do the RMS value, the time period you see here, it now becomes pi, because the pattern repeats after every pi. So 1 by pi, so therefore we put here the time period is 1 by pi, integral 0 to pi b square into d theta. What is b? B is once again Vm sin of theta. We can either keep it as theta or omega t, both are the same. So 0 to pi Vm square sin square theta d theta whole power half, because it is the square root of that value. So Vm square you take it outside, 1 by sin square theta, trigonometrical expression, sin square theta can be represented as 1 minus cos 2 theta divided by 2. So now we have to integrate that. So when we integrate, Vm square by pi is taken outside, 2 pi, 2 is also constant, so we bring it outside. 1 into d theta is, integral of d theta is theta, when we have cos 2 theta, minus is put here, cos 2 theta integral is sin 2 theta divided by 2. Now the limit is once again 0 to pi. So when you give this one here, Vm square 2 pi is kept constant. When you apply here, this will be pi, and then sin of 2 pi, it becomes 0. Once again if you put 0, theta is 0, then sin of 2 theta once again 0, so we get only pi here. So this is only pi here, and whole power half, that is square root. So we have here Vm square pi root is Vm, 2 pi, pi and pi will get cancelled. So root of 2, it is 0.707 Vm. So this is the RMS value of the sine wave. So what is the difference between the average? Average value is 0.63 something and RMS value is 0.707. So it is slightly higher than the average value, although it is not equivalent to the peak value. But peak value we generally don't take, because peak value of any signal may be the same. For example, if you take this is a sine wave and let us take a square wave. Both are periodic waveforms. Now let us assume that the square wave has the same peak value as the sine wave. So we have the square wave here, sine wave here. Let us say it has the same peak value as the sine wave. So when you represent this as a peak value Vm, when you represent this as value Vm. So when you say AC quantity of value equal to Vm, which is the peak value, what is the difference? We don't know whether it is a square wave or a sine wave. Both has the same peak value. So it's not very effective in representing the AC quantity. Whereas the average and the RMS value of these two waveforms will naturally differ. But better than average value, we go in for RMS value because it gives an equivalent effective value of a DC corresponding to the AC, and it is very convenient to use. Therefore, in most of the meters, we use only RMS value. The meters measurement, the lab, you are doing the lab exercises now. From this we will do lab exercises in AC. So all the voltmeters and the ammeters which measure the current and the voltage, they are all RMS quantities. You already know what is a vector. Vector is the one which has a magnitude and an angle and a direction actually. Magnitude and a direction. Now this is, let us say this is a waveform. This has a particular magnitude. Okay, let us say maximum value. So that can be represented as a vector with that value. So if we say this is Vm here, so the length of this vector will be Vm. You can see I have just drawn waveforms of various magnitudes, peak value. So this has got a higher value, so that is equivalent to this length. Similarly, this is the amplitude, that is the length of the vector. So basically a vector is the one which has a magnitude and a direction. Or we can say angle. In this case all are at 0 angle. Now let us see how this can be related to a sinusoidal function. We call here it is a phasor rather than a vector because we actually take a phasor to be a rotating vector. AC is not a constant magnitude. It keeps on varying its magnitude and keeps on moving around. That's why it has this theta, we know it is represented as omega t. It has certain angular speed. So therefore it is a constantly moving vector. So therefore we call it a phasor, which is nothing but a rotating vector. Why do you want to have this phasor? It is actually, a phasor is nothing but a mathematical tool here. Mathematical tool which will represent both the magnitude and the phase angle of the AC quantity. This representation of the AC is very convenient for us during the analysis of AC signals. That's why we are representing as a phasor or a vector. Now rotating vector, it is of course, once we say a phasor, it has a magnitude and a fixed angle. So therefore obviously it will become a complex quantity on the real and the imaginary axis. So here let us see here a rotation of a vector. This is a vector. This is actually a vector, but when it is rotating it becomes a phasor. Now let us take a vector of length Vm at some angle phi. So this vector is rotating in this direction. That means at time t is equal to 0, it is occupying this position. So at time t is equal to 0, it is projected at this 0. It has some value here, this value. At time t is equal to 0. Now as it rotates, it takes different values. So let us say it comes here, comes to this point at t is equal to t0. When it is projected onto the time axis, this time axis, we have at t is equal to t0, it has some other value. Obviously when it is here along this imaginary axis, this is the real and imaginary axis. So when it is here along the imaginary axis, it attains the maximum value at this point, which is here. So as it rotates, it occupies various positions here. So this is a conversion from a complex graph into a time graph. So this is how the rotation of the AC is represented, or this is how this waveform can be translated into a rotating vector form or a phasor form. So therefore this first graph is a phasor, and there is nothing but a projection on the real axis with respect to time, which is a simple AC waveform which is represented as Vm sin of omega t plus phi. Now we understand what is this phi. This is the phase angle. See here, this is the phase angle, the initial phase of the AC quantity. Now the same thing, when it is represented as a phasor, it can be written as V of t is Vm at an angle of phi. Actually when you represent it as a phasor, we don't put V of t, we give a vector notation. We put a bar there, V bar. So that is Vm at an angle of phi. This Vm is the magnitude of the AC and this phi is the angle of the AC. Vm at an angle of phi. Most cases when we do later some problems related to AC circuits, this will not have this Vm, we'll instead have the Vrms value, because as I told you, the RMS value is the measured value, and whenever we have a circuit, we measure the RMS value. Instead of using a peak value, usually we have the RMS value. Now, we'll know a bit more about the complex quantity. So, we know that the phasor is nothing but a complex quantity which has a magnitude and a phase angle. So, this is the magnitude is R. So, this is the magnitude, this is the phase angle phi. Now, when there is a magnitude and the phase angle, and when it is projected onto the complex plane, the real axis here and the imaginary axis along the y-axis, this is actually R, and on the real axis it takes a value of x, on the imaginary axis this magnitude projected onto the real axis is x, projected onto the imaginary axis is y. So it can be complex numbers, you should have learned complex numbers already. It can be represented as a rectangular form or a polar form. At a rectangular form it is x plus real value plus j of imaginary value, x plus jy, and a polar form is r at an angle of phi, and we also have an exponential form which is r e power j theta. This we generally will not use very much. We use rectangular and a polar form. How to convert from one form to other? If we have given the x values and the y values, we want to convert it into, if you want to convert this r at an angle of phi into rectangular value, we can take it as r cos of phi plus j sin of phi, because r here, r cos of phi is x, r sin of phi is y. So r cos of phi plus j sin of phi. When you want to convert this polar rectangular form into polar form, we have this r. Given the values of x and y, how to calculate r? It is a right triangle. By Pythagoras theorem, r is root of x squared plus y squared, and phi is equal to tan inverse of y by x. So it's a simple mathematics approach in order to represent the AC waveform, and we need to know all about these conversions from polar to rectangular, rectangular to polar, in order to make use of them in the AC analysis. Just a small example here. We have a polar form phi at an angle of 36.87 degrees. We want to convert that into, say, rectangular form. So how do you convert that into rectangular form? Phi of cos theta plus j phi sin theta. So phi cos of this one is 4 real component, phi sin of this angle is 3 imaginary component. So we have 4 plus j3. We want to reconvert that into rectangular form. We know that it is once again a right triangle. This is what is represented here. 4 plus j3. So this is 4. This is j3. So this is the vector here. And this is the angle. So this value is actually 5 and this value is 36.87 degrees. Now when you want to reconvert that into this rectangular form into polar form, we need to take it as right triangle, which 4 here and 3 here. The root of 4 square plus 3 square is equal to 5, and then this one is tan inverse of y by x, which is 3 by 4, 36.87 degrees. So we get back the polar form. Just a simple exercise to know the polar to rectangular, rectangular to conversion, polar converters. Most of the calculators, functional calculators which you will be using, they have a direct conversion. There is a symbol called polar to rectangular, rectangular to polar conversion. You can make use of that. And some calculators will have complex mode that you can select. When you have the complex mode, you need not even convert from polar to rectangular. You can just simply use all the complex numbers to add them, divide in any form. But it's always better to use the normal mode, not the complex mode, because if you forget to change, then it will have problems while doing numerical examples. Now more about phasors. Now the phasors, I told you, they are very useful for analysis of AC circuits. That means we are converting a waveform into some mathematical expression. From the time, waveform is in time domain, because we are having the waveform as varying magnitude with respect to time. So from the time domain, which is given by V of t, Vm sin of omega t plus phi, we are converting into phasor domain, which is, see, we have here the bar. It is a vector V bar as Vm at an angle of phi. This is a phasor domain, or this is also called a frequency domain. Both are the same. Phasor are the frequency domain. So this is how the time domain is transformed into phasor domain. Because when you do analysis, it's very hard to analyze with the signals. If you create that into a mathematical expression using a phasor domain, it's very easy to manipulate those values. Use those values in the calculation. So the amplitude and the phasor difference are the two important concerns in the study of voltage and the current. These are very, very important. This will later help you how to find the phase difference, what is the significance of these phasor notation in calculation. So the basic difference here between V of t, that is the time domain value, and frequency domain. So V of t is instantaneous and the time domain value, and V is actually we have to put it as V bar. V is actually a phasor domain. V is time dependent. This is not time dependent, and V of t is always real and there is no complex term. It varies with respect to time. Here there is no variation with respect to time, but it is always complex. So the time variation, actually we are converting it into a complex quantity. So this phasor analysis applies only when the frequency is constant. That is, you know that throughout Australia the frequency is always 50 Hz. So when you do the circuit analysis, it's easier to maintain everything at 50 Hz, and we can simply represent them as a phasor notation and then add or subtract or do anything with the values. It's easy to write programs, it's easy to analyze everything. Whereas if you connect a 60 Hz supply with a 50 Hz supply, then the phasor analysis will not be valid, because the phasor and the phase differences are applicable only to waveforms of the same frequency. So that is the important point you have to know. This sinusoid applies only if they have the same. Next is phasor difference. What is the phasor difference? Now that you know what is a phase. What is a phase? The angle made by the waveform at that instant of time. Okay. Now we have here phasor difference. So let us here there are two waveforms. See, there is one waveform A and B. A and B are overlapping with each other. They are both the same. Exactly, they start at the same point. They follow the same point. The magnitudes are also the same, and they end up at the same point, A and B. So that means the phase shift is 0 degrees. A and B are in step with each other and they do not move away from each other. So we have a vector A represented like this. Vector B is also represented like this. Both are in the same direction and of the same length. Now the next is, this is actually, you know, all these are sinusoidal waveforms. This is pi here, this is 0 here. At the center we have pi by 2 maximum value. Now A starts at 0 angle and then it goes like this, and B starts at an angle of pi by 2 later, after A. Starts later, after an angle pi by 2, and then it continues. The magnitude of A and B remains the same. The peak magnitude. So therefore we see now here B starts pi by 2 later than A. So that means the phase shift between A and B is 90 degrees. Now which starts first? A starts first and then B starts. So we put instead, earlier we were putting A like this, B like this. Now A starts first in this direction, B in this direction. This is actually the leading direction of, this is actually the leading direction. So if you write here A in this fashion, A starts first. A is leading. A waveform is leading and then only B comes. So A is leading B. Suppose we represent A like this here, in this direction. So start A as reference, put A in that direction. B is starting pi by 2 later. So you have to put B in this direction. So this is once again 90 degrees. So either you can represent this way or this way. Whatever it is, this A should be always leading, and this is the direction of the leading waveform. Now the next in this case is B starts first and then A. Once again it starts at an angle greater than pi by 2. So it's the other way around. Once again it is 90 degrees. B starts first and then A comes. So here it is put in this way. So if you take A as a reference once again, in this case if you take A as a reference, B actually has started earlier than A. It is leading. Okay, so leading direction. We have to put B. So you can take any waveform as reference and represent the other waveform with respect to the reference waveform. Now the next case is G is like this, A is totally out of phase. So when D is positive, A is negative and vice versa. So it is totally 180 degrees out of phase totally. So it is 180 degrees phase shift. So when A is in one direction, B is in the other direction. Once again, it depends. Usually, whichever starts with 0 is taken as the reference. In this case, A and B are both starting at 0. They are in the same angle. Reference is always along the x-axis. Now in this case, A is starting, so A is taken as the reference. It is usually better to represent A like this. And B will be actually lagging. B is starting later. So it is lagging. So you put like B like this. In this case, actually B is the reference, so it is always better to represent B like this. Because reference at 0, whichever starts is taken as reference. A is actually once again lagging. Okay, so A will be in this direction. Now, here again B is reference because it is starting at 0. So B is reference. A will be 180 degrees out. This is how the laser difference between the two waveforms are represented. Now once you represent it as a vector, it is easy to write the mathematical expression as V at an angle of 0. In this case, it will be A will be at an angle of 0, B also 0. In this case, A is at an angle of 0, B is at an angle of minus 90 because it is lagging. In this case, B is at an angle of 0, A is at an angle of minus 90. Here B is at an angle of 0 and A is at an angle of 180. Minus 180 or plus 180 are the same. We can represent it any way. So this is the phasor difference here shown in the waveform. So far we have seen at some angle 90 or 180. This is for some other angle 5. So we have one voltage V1 which is starting at reference 0. It is going to sine waveform. I told you can compare phase difference only when they have the same frequency. That is always for the positive half there should be pi angle and for the negative half that should be again another pi. Now there is some other waveform here V2 which starts here at this point. So it starts earlier by an angle of phi. Now I told you whichever starts with 0 is generally taken as a reference. So here V1 is taken as the reference and V2 is shown like this. So the angle is phi. So this is the phase difference in the difference here, there is one waveform V, actually a vector V represented as Em at an angle of phi, and there is another waveform I at an angle of minus theta. So how will you first represent on the real and the imaginary axis? We have V at length Em, angle of phi, and I is a length I at an angle of minus theta. So it will be obviously the fourth quadrant, minus theta. So what will be the phase difference between the two? Next phase difference is this angle, theta plus phi. The magnitude of the phase difference is theta plus phi. So this is how you represent the phase, where you compare the phase difference. It's now easier in this case rather than putting it in the waveform and finding out what is the phase difference. Each is starting at some other angle. It's always easier to represent them as a vector and adding them up together. Or if this also falls in the same direction, what will happen now? Suppose I have I as Im at an angle of theta. So where will be Im at an angle of theta? Im at an angle of theta will come here. So this will be I. I will be Im at an angle of theta. So in this case, what will be the phase difference? The phase difference will be actually this is theta, this is phi, only this is the phase difference. So phi minus theta. This is the phase difference will be phi minus theta. So it's always easier to find the phase difference by projecting the AC quantities as phasors rather than waveforms. Now some more problems here. We have 2. We have to find out the sum of two values. See, I1 of t is one waveform, which is a cos waveform. I2 of t is another waveform, sine waveform. So if you want to calculate the sum of these two waveforms, it's always very hard to find out using the waveform notation or the time notation, time domain. It's easier to convert them into phasor domain and add them together. So how to convert that into phasor domain? First convert this cos into sine. Once again using the notation, cos omega t will be sine of omega t plus 90. So sine omega t plus 90 plus 34. So it will be 90 plus 30. It is 120 degrees. There is a mistake here. What is sine of this? All silver teacup. So sine of omega t plus 90 is, sine is positive. That's correct. So it is sine of omega t plus 90 plus 30. So it is actually 4 at an angle of 120 degrees. So this will be 4 at an angle of 120 degrees. Sorry. This is 4 at an angle of 120 degrees. And then here you have I1 of t is directly given as a sine quantity. So it is 5, angle is minus 20. So 5 at an angle of minus 20. So when you add these two, 4 at an angle of 120 and 5 at an angle of minus 20. So how do you get this value? You have to use the conversion. You cannot add the polar quantities directly. You have to convert that into polar quantities, I mean rectangular quantities. So this will be 4 into cos 120 plus a sin 120. This will be for this waveform, and for this one it will be 5 into cos minus 20 plus a sin minus 20. So once you calculate these values, now you can add the real values together, imaginary values together, you will get something like x plus jy. So when you have something like x plus jy, how do you convert that into polar form? The magnitude will be root of x square plus y square, and the angle will be tan inverse of y by x. Now in this case you will get only plus here, so it will be in the first quadrant, so it is simply tan inverse of y by x. Now what is the relationship of the phasor for various circuit elements? In this case, phasor relationship means we mean the relationship between the voltage and the current. So let us take a simple resistive circuit. We have one resistance, a voltage VC is the small v, so it is a sinusoidal signal applied, and then a current of I. This is actually I means V of t, and this is I of t. Now how to see the phasor difference between the voltage and current when you have only resistance connected in the circuit? Now what is current? Let us say current is expressed as Im sin of omega t plus 5. Now according to Ohm's law, we have V is equal to I into R. So R into, I am writing the expression for this I, Im sin of omega t plus 5. So therefore V can be represented as R into Im at an angle of 5, and I is also represented as Im at an angle of 5. So otherwise we can say V is equal to R into Im at an angle of 5 is equal to R into I. So therefore if you project it along the real and imaginary axis, now the vector I is nothing but I at an angle of 5. Im in this case. Length is Im. This is the I vector which has a length of Im at an angle of 5, and voltage is also a vector which has some other length equal to V, in this case will be equal to R into I. R into I. Once again same angle 5. So in this case, that means for a resistor we can see that the voltage and the current are in phase with each other. That means the phase angle of the voltage and the current in a pure resistor is the same. Only the magnitude of voltage and the current differs, of course. Depends upon the amount of resistance connected. Next, for an inductor, we are connecting a pure inductance here. Once again we are applying AC voltage V of t, and then a current of I of t flows through that. Now let us take once again the current as reference, Im sin of omega t plus 5, which means the current is nothing but I can be written as vector I can be written as Im at an angle of phi here. Now V for inductor, the voltage is L into di by dt according to Faraday's law. So when you differentiate this time ddt of this I value, we have Im is constant, L is already there. Sin of omega t will be cos omega t into omega. So cos of omega t plus phi omega comes here. Now omega L into Im sin of omega t. I am converting this cos into sin because then only we can compare the waveform. So cos of omega t sin of omega t plus 90. So omega t plus phi plus 90. So this one Im sin of omega t plus phi is nothing but current I. So therefore omega L is an extra feature here. Omega L I, and we have a 90 degrees. So it is an angle of 90 degrees, or we can say J omega Li. Okay. So therefore, because one and an angle of 90 is nothing but same. So that is the relationship between the voltage and the current. The voltage across the inductor is equal to J omega L into I. So if you represent that in the vector, let us say I is there, given I at an angle of Im at an angle of phi. Now voltage is plus 90 degrees. That means voltage leads. Leading is always in this direction. So the voltage leads the current by 90 degrees. Or as we can say, in the inductor, the current lags the voltage by 90 degrees. This is the voltage. Usually voltage will be taken as a reference. So it's always mentioned like this. I lags the voltage by 90 degrees. Now next one is the capacitor. In the capacitor we are taking expression for V as Vm sin of omega t plus phi, because it's always easier to calculate I as C into dV by dt rather than taking V as integral of I dt. Rather than performing integration, we can do a differentiation here. So we know that I is equal to C into dV by dt. Now we have omega. If you differentiate this, once again omega C is there, Vm is constant. Sin of omega t is cos of omega t into omega plus phi. So omega c Vm, sin of, convert this cos into sin. So sin of omega t plus 90. So it is C Vm, C into Vm at an angle of omega c Vm. So here omega c into Vm at an angle of 90, because this is taken as angle of phi. This will be angle of 90. Because this is Vm. So J omega T. So if you represent that here, a voltage is taken as a reference, which is at an angle of phi, and the current is leading here. The current is leading at an angle of 90. So in this case, we say that the current leads the voltage by 90 degrees. So these are the basically three circuit elements: resistor, inductor, and capacitor. So in the resistor, the voltage and the current are in phase with each other, or we can say the current is in phase with the voltage. For an inductor, the current lags the voltage by 90 degrees, and for a capacitor, the current leads the voltage by 90 degrees. So this is put together here. We have a resistive circuit. For a resistor, voltage and the current are in phase with each other. For an inductor, the current lags the voltage by 90 degrees. And for a capacitor, the current leads the voltage by 90 degrees. Summary of the relationships: time domain and the frequency domain. So this is small v here in the time domain, which represents time difference d of t and I of t. In the time domain it is Ri. The frequency domain is capital V Ri. I mean, usually the vector, the bars will be neglected. It's understood that it is a vector quantity there. Now this is L into di by dt. Instead it becomes a imaginary quantity. Differential becomes a imaginary quantity. J omega Li, and similarly T into dv by dt. So it becomes 1 by J omega I divided by J omega I. Now just a simple resistive circuit. We have here three different voltages at various magnitudes and angles here. Now it is passing through 10 ohms. Now we have to find out the current through the resistor. How will you find? You have to add all these voltages, and the current will be this voltage divided by the resistor value. So we have to just add all the voltages. So V total is each of the voltages 22 at an angle of minus 64, this one plus this one. So 15 at an angle of 0 will be 15 plus J0. 15 cos of 0 plus 15 J15 sin of 0. Now 12 at an angle of 35, once again 12 cos 35 is this one, 12 sin 35 is this value. Now 22 at an angle of minus 64 is 22 cos 64, 22 sin 64, and this is minus, so minus. Sign of minus is minus. Now we add all the values, add all together the real values, add the imaginary values together. This will be the net voltage. Now convert that voltage into polar form. So how do you convert? Once again, in the polar form, this will be root of say 34.5 square plus 12.9 square. So that value will be something like this, 36.8052. The angle will be minus 20. How do you calculate the angle? So draw the quadrant here. Plus 34 is along this axis, minus 12 is along this axis. So it is like this. So if you take tan inverse of, this is the angle actually. So tan inverse of this value divided by this value, you have to take it as negative, because it is in the fourth quadrant. So it is minus 20. Therefore, what will be the current? Current will be this 36 divided by the resistor was 10. So 36 divided by 10 will be 3.2 at the same angle, because in a pure resistor the voltage and the current are in phase with each other. So this is the resultant vector shown. 15 at an angle of 0 is like this, because this is the reference. This is the reference taken. So 15 at an angle of 0 will be in this direction. 12 at an angle of 35. Actually we are starting from here. 22 at an angle of minus 64. If you take this point as reference, 22 at an angle of minus 64 will be, this is minus 64 is here, and to that we are adding 12 at an angle of 35. So this becomes reference. This angle will be 35. So at 35 you put a vector of length 12, and then here 15 at an angle of 0. So it is along the x-axis. So the resultant vector will be this voltage. This is the voltage V, which is actually 36.8 at an angle of minus 20.3. So this is the vector representation of all the three voltages added together, and since it is a pure resistor, we see that it is just directly dividing the magnitude of the voltage by the resistance. It gives you the current. The angle of the current remains the summary of the topic today. What did you learn today? We saw that AC is nothing but a sinusoidal waveform, because it can be expressed as a sine of theta or cos of theta. It can be represented as peak value or a peak to peak value, the average value or RMS value. RMS value is mostly used as it gives a close equivalent to DC. So it's a very commonly used value of the AC waveform. AC is more conveniently represented as a phasor rather than keeping it as a waveform, because analysis is very easy. So this provides frequency, easy of analysis, because it is in the frequency domain. Phasor can be represented as a polar or rectangular quantity depending upon what you need to do. If you want to add or subtract, we retain it as a rectangular quantity. If you want to multiply and divide, we can have it as a polar quantity. Now, for a resistor, the current is in phase with the voltage. For an inductor, the current lags the voltage by 90 degrees. And for a capacitor, the current leads the voltage by 90 degrees. These are the three important points you have to remember, because when you have when you do the actual circuit analysis, we'll have resistors, inductors and capacitors all connected together in AC circuit. So you should be very careful to find the combined effect. Only for a resistor it is in phase. For an inductor it is out of phase or lags, the current lags the voltage by 90 degrees. And for a capacitor the current leads the voltage by